Thank you so much. Thank you so much for coming. I didn't expect so many people in such a rainy day, but very nice to see everybody here. So today I'm going to talk about a little bit about our research on making robot learning work in the physical world. So here in my talk title, I use the word gravity just as a simple example of all the real world dynamics that a robot needs to kind of experience and deal with when they're deployed in the physical world. And as you'll soon see in this talk, this dynamics can either be your friends or enemy, depends on how you treat it. And we just recently updated our logo with the Stanford logo. Cool, let's start. So I will start with one of my earlier work that's really got me into the field of robotics. So this is in year 2017 when we were collaborating with MIT, in particular Alberto's group, participating in this Amazon Robotics Challenge. So as you can see in this video, this robot is actually able to deal with quite a large variety of objects, right? Eventually it's able to kind of pick up all the objects in the bin. It's piled with random objects, and then you clean up the bin and finish the task. But one thing that might bother you a little bit, it definitely bothered me a lot, is how slow this robot moves, right? So I actually didn't speed up this video just so that you can feel the slowness in the real time. However, if you ever get a chance to visit the real warehouse and then see how people are actually doing this task today, you'll just realize that humans are just on a whole another level. Right? So for example, this worker kind of just snatching the packages, toss them around, sort them into the right location. And everything here is highly dynamic and chaotic, but fast and efficient. So what is the difference? So I think fundamentally, actually, we can categorize these two types of manipulation, manipulation strategy, into these two categories. One is quasi-static manipulation, the other is dynamic manipulation. So what is the difference? Right? In quasi-static manipulation, the basic assumption is that we assume the world stops as soon as the robot stops. Right? So that actually makes sense when you're grasping an object and moving slowly. So this kind of quasi-static assumption is very convenient and help us to simplify a lot of planning problems. Because under this assumption, everything that you need to care about is just the geometry of the objects and the kinematics of your robot. And you can simply ignore other physical properties about the object. However, on the other hand, dynamic manipulation is very different, right? Instead of trying to explicitly avoid dynamics, you try to leverage the dynamics, for example, the force of acceleration, in order to more efficiently manipulate object, like tossing object around. So as a result, when it works, the system oftentimes is much faster and efficient with dynamics in the loop. So the goal of our research, at least a lot of them, is trying to move our robots from this quasi-static domain to this dynamic manipulation domain. So the question is, what's making it hard, right? So is that hard to move robot fast? Well, I guess first, some good news. I guess thanks to decades of research in mechanics or robot design and also control, today we do have robots that can move very fast and precise. And you can easily code up a demo like this. This robot is going to pick up this little pen, toss it precisely into that little cup. And it can able to do it again and again. However, the catch here is that this demo will only work for this one particular object and this one target location. In fact, the whole system doesn't even need to have a perception system in the loop. And the trick to make this demo work is that you just let the robot toss the object and then see where the object lands and then put the cup there and it will work. And then it will work again and again. Right? So what this example really showed us is that today we are actually pretty good on modeling the robot's internal dynamics, right? Making them move fast and precise and making them repeatable. But the real challenge, or the remaining challenge, really lies into modeling those unstructured external world outside the robot, like the object dynamics or the environment, where the diversity and the complexity is significantly higher than the robot itself. So that is also where our research focuses on, modeling the external world. Okay, so how to model the external world? So I think if you look at the literature, we can see that over the years, we have seen a lot of different work that's trying to derive different analytical models or dynamics models for different robotic systems or objects. Right? However, I think one thing that has been missing or remain as an afterthought is the perception. Right? Oftentimes, if you look at all this work, perception is still remain as an afterthought. That's either considered just like simply out of the scope of the study, or they are assumed to be a near perfect state estimator for those analytical models. But what is the state of the system? So I think if you look at most of the papers or works, I think they oftentimes try to use object pose as a description of the state of the object, therefore the state of the environment. However, this kind of definition of object pose kind of only makes sense when you're dealing with rigid objects with known geometries. However, on the other hand, our world is often filled with objects that the system has never interacted before, like unseen objects, where their state or pose is oftentimes ill-defined or impossible to measure. So for example, just consider how you're gonna model or formulate the state of a crumpled class. Then how about a pair of random leaves? Not to mention their physical properties like the mass, friction, or stiffness, that is even harder to measure. But at the same time, if we try to take a step back and then think about how we as humans are able to interact with all these different objects, it's not like we are spending all our brain power trying to estimate the pose of every single leaf in this pile in order to interact with it. Right? So instead, what we really rely on is a sense of intuition, where years of our experience interacting with the physical world let us learn a mental model of dynamics, where this model may not be perfect or very accurate, but it's sufficient enough for us to interact or plan our action of how to interact with all these objects. So the goal of our research is try to impart our robots with a similar type of intuition, where it allows them to learn from their physical experience, leveraging closed-loop feedback, all from raw sensory data like pixels. And here is actually an example of system that's able to leverage dynamics in their manipulation. Right? So in this tossing ball case, by using this dynamic tossing action, the system is not only able to be more efficient than a typical pick-and-place system, it's also able to effectively extend the robot's reach range, putting an object that's further away than its maximum reach range. So that is also the true advantage of using dynamic action. And in our lab, we actually have been studying many different ways that you can leverage dynamics in the process of robot manipulation. And then really while we are working on all these projects, what we're really going after or look for is this general recipe to allow the robot to learn this kind of physical intuitions through their physical interaction. And today I'm gonna try to use some of those projects as example to help us re-examine the relationships between perception, action, and modeling, and then really think about how powerful tools like machine learning is able to help us to address some of those most challenging problems. So first, I will start with a project called FlingBot. And then in this project, we're gonna look at how we can just allow or enable the robot to directly learn the dynamic actions from the raw sensory input, like pixels, without an explicit dynamics model. Right? So here we're actually going to deal with objects that has very complex dynamics, like deformable objects. And then I think most importantly, we also want to use this particular example to see what is possible under this formulation, and also what are the limitations with this formulation. Okay. So the task that we're trying to study in this project is called class unfolding, right? It's very simple. Just given any class or crumpled whatever, we want to increase the overall coverage of the class. So you may not feel it immediately, but actually doing this task on a robot that's given any class under any configuration is quite challenging for many different reasons. So for example, first is that whenever you have a system that's kind of dealing with deformable objects, in particular fabrics, you often need to deal with very complex dynamics because of their very high degree freedoms. Right? Oftentimes people even say that deformable object like class has near infinite degree freedoms. And also what makes things even worse is that among all these possible degree freedoms, the robot only has a direct control of a small number of them. Right? So for example, when the robot is kind of holding up this piece of class, all it can directly control is a small region around the gripper, like which is in contact. However, the rest of the class is just kind of hanging there, and the robot does not have direct control over those positions, right? Those out of contact parts. So in other words, whenever you have a class of fabric in the system, you're dealing with a highly under-actuated system. So that is another challenge. So because of all these like special properties about deformable objects, this typical action primitives that people code up for handling rigid objects is oftentimes not sufficient. Right? So for example, the pick and place action is oftentimes not sufficient because each action can only affect a very small region on the class. And if ever this class is larger than the robot's maximal reach range, then we are never able to actually fully unfold the class, unless your robot can climb over the workspace. So as a result, I think this choice of using only quasi-static action for deformable object manipulation has really become this kind of shared bottlenecks for a lot of prior works in deformable object manipulation. So as a result, despite there's a lot of progress on like improving the model and also the method in modeling modeling the deformable objects, we often see that the resulting system is still highly inefficient and can take hundreds of steps just to unfold a very small piece of class. So here is actually showing an example of this robot using in total 300 steps to unfold this very small piece of class. But obviously that's not how we human will do this task. Right? So instead, we're gonna more likely to do something similar to this, where you're gonna graph this class with your tool arm and then unfold it with a single fling action. Right? So in this particular example, basically what we are doing is to leverage the accelerations in our action in order to control those out of contact surfaces, which is highlighted by the red, the green arrows. So with this simple observation, the idea of a fling ball is actually very simple. Basically, let's use those high velocity two-arm fling actions for class unfolding. And here is the system in action of FlingBot, and also in comparison with the pick and place system. And then in the bottom, we plot out the class coverage with respect to interaction steps. And you can see that with FlingBot, with the fling action, the system is able to quickly unfold the class within just 2 steps, while the pick and place system actually will take much longer time, making smaller progress. That's pretty straightforward. So the bigger question now is how we can make a system like FlingBot work. So I think here, instead of just talking about FlingBot system, I want to use this opportunity to kind of talk about some general strategies that we oftentimes apply for like making machine learning algorithm work in the physical world. So we all know that machine learning needs data. Oftentimes, the more data, the better. But we also know, at least for people who work with robotics, know that data for robots is really hard to get. And not only because it's oftentimes involved the physical robots and they take time to set up and also collect data, but also the challenges come from labeling those data, right? So if you want to label those raw sensory inputs with the proper or correct robot actions, it's oftentimes a non-trivial task for a typical human, right? Unless you're trained roboticist. It's a different task than, for example, just labeling cats and dogs for an image. You need a roboticist to provide the correct label for those data. So as a result, in our method, we always try to, one thing that we always try to do is try to bridge this data gap from both ends. And so for example, from the one end, we'll try to scale up this data collection process by using self-supervised learning. And in particular, once you have a robotic system, it's actually very natural to apply the self-supervised learning idea, in particular because your robot has the natural ability to interact with the environment and observe the effect of the action. So as a result, you can make use of the future observation for the state or for from your sensor as a supervision signal for the current action. So for example, in the FlingBot case, after every fling action, we actually use the top-down camera to look at the class coverage and compute the delta coverage as a reward signal for every fling action. And similarly, in the tossing ball case, we also can set up a top-down camera and observe where the object lands and use that as a supervision signal for every single tossing action. And then, most importantly, when you are combining those self-supervision signal with the auto-reset mechanism, you can actually allow the system to collect training data 24/7 without human intervention. So I think in particular, here is how the tossing ball reset. I think that's pretty cool. So that's actually how we can scale up the data collection with the physical robot system, right? By using observations of future states as the label. On the other hand, we also oftentimes try to kind of leverage the structure or the inductive bias in the problem in order to improve the sample efficiency or learning efficiency of the algorithm, so that the system can learn an effective policy with not too much data. So one of the popular or like a common structure that we like to use in our network design is actually what we call spatial equivariance. So this is actually a very simple structure in the problem, but it's actually a very common structure that appeared in many robot manipulation tasks. So what is spatial equivariance? It basically means that if you apply a spatial transformation on your input observation, let's say images or the objects that you observe, it should result in the same spatial transformation on output action. And then here the function f is the policy that we want the robot to learn. Right? In particular, in the context of Flingbao, what the spatial equivariance means that is if you transform the input image, let's say translated by a certain amount, it should corresponding to the same translation applied on the output action. Right? So that is for translation. And then similarly, we have this spatial equivariance for the rotation operation and also scale. And then actually, if you formulate the action parameterization properly, you actually can observe this kind of spatial equivariance in many other robot application or manipulation tasks. For example, pushing, grasping, or even navigation. And then I think sometimes we found that it's such a common structure and some common generalization capabilities that we hope the system or the policy to be able to learn. But you'll be surprised that many of the learned policy today are not able to perform this very simple type of generalization without a lot of training data. So how we can leverage this structure, right? So one typical method that we have been using quite often in our work is what we call spatial action map. Right? So instead of trying to directly predicting the action parameter as a vector, we actually instead trying to predict a dense value map for all the actions, where each of the output pixel will corresponding to the single grasping action that's centered around that pixel. So why is a good formulation? Because by using this kind of fully convolutional neural network, we can naturally get a little bit of the translational equivariance. And then by explicitly transform the input image by, for example, applying rotation and scale, the network can also obtain like rotation and scale equivariance as well. So all that means is that in the end of the day, the network only need to learn the value function for a fixed action parameter. For example, grasping in the middle with a horizontal angle, and it can immediately generalize to all other action parameters by applying it into a transformed input. So this kind of generalization capability is what enables us to drastically reduce the data needed for training this value function. So that is the core idea. So, and obviously, I think I have to mention that there's actually many other ways that you can leverage a spatial equivariance in your policy learning. Spatial action map is just one of the simplest example. And actually, recently there is a lot of work that's studying equivariant network that can be applied for robot policy learning or improve the learning efficiencies for robot policy. And I think this is an interesting direction that I encourage you to check out if you really care about sample efficiency or learning efficiency for your robot policies. And I think one exciting part about all this later work is that they can allow us to extend the action space to continuous and 3D actions instead of the 2D action that I have shown you earlier. Okay, so in the end of the day, we can train Flingbao with data that collected by itself, and then in the end, they are able to achieve over 80% of coverage within 3 interaction steps, and they're able to generalize to unseen shapes when they only train a rectangle claw. Right? And also, it can able to unfold claws that's larger than its reach range, which is something that standard pick-and-place system cannot perform. So I think to summarize, what's really surprised us in the Flingbao system is basically question?
Yeah, for the spatial action map, is like the velocity of the end vector encoded in that somehow?
That's a good question. So the question is, in the spatial action map or the policy learning, do we formulate the velocity? In our final model, we didn't predict the velocity. We actually basically just use a fixed velocity. So network only learn where to grasp And that's the most important part. We actually did do an ablation in our paper that's also predict the velocity. It improved the performance a little bit, not too much. So that's why we actually didn't include that in the end.
So the approach I think you've taken is you sort of engineer the equivariance into the network itself. But
Yeah.
I guess there's a complementary approach in computer vision, which is that you predict action parameters but augment the data. So what are the trade-offs?
Yeah, so actually, if you think about it, our way of achieving equivariance is actually equivariance through augmentation. So we basically augment the training data, but we also augment the output. So I think if you think about computer vision tasks, oftentimes you're learning invariance. You augment the input data and you want to output the same output. But in our case, is that we augment the input, we also want them to change the output because action also need to rotate at the same time. Mm-hmm. So it's very similar. We basically achieving equivariance, not exactly through the network design, it's through the augmentation. Yeah. Cool. Any other questions? Great. So I can summarize FlingBot. I think the most important takeaway that I hope that you guys can take away with is how simple the system is, right? So we actually did not model the states or like trying to model the dynamics of the class at all. So for example, we never try to reconstruct the mesh of the class or detect its pose or detect key points. The system only takes in pixels and is able to perform pretty well. And I think this simplicity really underscores or highlights the advantage of using dynamic action for the task of deformable object manipulation. And fundamentally, what it allows us to make is to make use of the accelerations in our action in order to control those out of contact surfaces. Question?
I'm just curious, did you guys stress test this with, let's say, like a plastic bag, not cloth, something that has like really weird dynamics?
Exactly. So we stress tested in our lab, and I can tell you that when the dynamics is very different, it won't work well. I think later I will actually show you some of the failure cases in our follow-up work. For example, just make your class really long or really heavy, it will not be able to work. And also back to the earlier question of why we're predicting velocity doesn't help that much, is because this robot just cannot achieve very high velocity to start with. So there's a lot of limitations around that. It has a small range of objects it can work with. Good question.
Just quickly, if I get it right, you're just predicting the where to grasp.
Yes.
So what is the motion?
The motion we code it up. We code up the primitive. Yes.
It's just like manually coded.
Yes, we manually code it up.
Do you think adding the cloth modeling the cloth will help it generalize to other things like plastic or heavy cloths?
It's possible. The question, let me try to repeat, is that if we model the class, will it help it to generalize? I think it's very possible. But here we didn't do that, and we kind of just show that if you just take the pixels, predicting where to grasp, it's able to work pretty well. But modeling it, as I was showing in the later part of my talk, like actually immediately after this, will help for generalization. Yeah.
So question about those manually coded primitives. So I assume that there you kind of tune the gains, right, in order for this to work. So I guess then, and you're sort of predicting the high level grasp thing, right? So how is the network sort of learning about the dynamics? Like I guess when you were describing it, I guess what I would have assumed is that you learn those gains or those parameters from data, because that seems like it would be hard for someone to manually engineer.
Yeah, so actually for this system, we don't learn those parameters. And then one way to think about it is that you kind of front load the complexity in the grasping stage. And then the actual fling action is pretty open loop. And then if you think about how we actually do the fling action, we don't actually do a very detailed closed loop control for the fling action. It's pretty much open loop. And then, but what we really need to plan on is where is a good grasping location. But I would agree that if we give the system an ability to adjust the gains and velocity, then maybe they all can perform a lot better and also potentially work for more objects. But we didn't do that for this particular work. Yeah, and it is a limitation that I will come back to. Okay, so, and also in this work, we kind of use this as an example to highlight what are some principles or general knowledge or useful lessons we can apply for applying machine learning algorithms into a physical robot system. But of course, those ideas will not be able to solve all the possible tasks and in manipulation. And here I want to highlight some of the limitations of FlingBot. Right, so one particular one I really want to highlight is the system's limited action precision. Right? Because when we train, if you still remember, when we train the system, all we can care about is the overall coverage of this class. That's the reward that we train on. So as a result, the system actually cannot really distinguish between different configurations of the end configuration for the class. And then all these examples I'm showing here will be considered as equally good for the system. And then the system actually does not have a control of how to achieve a particular goal configurations within this set. So this kind of problem, like limited precision, is probably okay for the task of class unfolding, but that's not okay for many robot manipulation tasks where precision is very critical. Right? So here is just an example. Yeah, so I guess we probably will agree that for a task like this, the precision of your action is very important. And then a method that's like we introduced in Flimba will not be sufficient. So why? I think fundamentally what's make these two tasks different is that for the later task, there are much narrower sets of goal conditions that we want the system to achieve, which is demonstrated by their high precision requirement. So as a result, it's much harder to learn an effective policy through random trial and error without any prior knowledge about the system. And so observed that kind of limitation and also motivated by this kind of a requirement, in the later part of, like in the second part of my talk, we're gonna focus on this category of task that has a much higher precision requirements in the manipulation process. And we're also gonna use this example to see that how a model that's like dynamics model learned from an inaccurate simulator is able to help us to like acquire this kind of precise manipulation skills. So in this part of the talk, we're gonna look at two types of tasks. Like, so for example, the first one is like trying to swing a rope to hit a particular goal. You can imagine that's a like simplified Jenga task that I showed earlier. And the second one is that we try to fling this class into a particular configuration. You can imagine that as a like more precise task or harder task of the earlier Flimba case. Right? For both tasks, the goal is defined by the key point, the target key point configuration or location, like the tip of the whip or the corner of the class. And because the goal is still outside the robot reach range, it still requires the system to use dynamic actions. So that is the setup or the task. And then as you can probably imagine, it is a very challenging task, even for human. Right? So we actually did this experiment in our lab. Given a rope that you have never interacted before, it's actually almost impossible for you to hit the goal in the first try. But the good thing is that oftentimes we observe after 2 or 3 attempts, the user is able to kind of hit the goal by like through a few trial and error attempts. So the question now is that what did we learn in this very limited attempts? Right? So how do we perform this task as human? So did we actually able to learn to predict the full forward dynamics model for this rope? I think that's very challenging. At least I don't think I can, right? So the rope trajectory is actually really complex, and I don't think we are able to predict it very precisely with just 1 or 2 attempts. And similarly, I think it's also almost impossible for us to actually decode or learn the physical parameters of the rope, like its stiffness or nonlinear densities, right? So that's actually very similar to the idea of system identification, although it's possible, but I think with this very limited data point, it's very hard. So instead, I think what we are really relying on is a sense of intuition about how we can adjust our action in order to affect the trajectory or the effect of the rope. Right? So for example, we know that if we swing harder, the rope will go higher. Although we don't know by how much or exactly how much, we know the general direction. Right? So instead, we can actually rely on this kind of intuition in order to help us to learn how to adjust our action in order to get closer and closer to the goal. So in other words, we hypothesize that the knowledge about this adjustment or this gradient of effect is much easier to learn and also transferable to different objects with different physical properties. So in this work, we basically try to distill this observational hypothesis into an algorithm called iterative residual policy. So at its core, we try to learn a delta dynamics model that basically will take in an observed rope trajectory that is tracked by a calibrated camera. And then additionally, we'll take in a delta action as an input, and then the model will try to predict an updated trajectory after you apply that delta action on top of the current action. So here, the robot action is modeled by their joint angles, the target joint angles, and the maximum joint speed. And the robot always starts with the same initial configuration, and then their action is basically modeled by a linear motion in the joint space. So as you can see, under this formulation, the model does not need to predict like the full forward dynamics model or predict the complicated trajectory from scratch, But instead, you only need to learn how to deform the already observed trajectory conditions on the delta action, which is a lot easier task to learn. So after we have this delta dynamics model trained, the next step is actually quite straightforward and simple. You basically can just like sample different delta actions and then do the forward prediction and select the best action to move forward and getting closer to the goal, right? So it's like a very standard model predictive control framework. However, one of the challenges I want to highlight here, or emphasize again here, is that we only can train this delta dynamics model in a simulator that is highly inaccurate. Right? So as you can imagine, for a task like this, sweeping a rope, the simulator is actually, there's a huge sim-to-real gap if you use like a standard simulator. So right now, I think for that project, we use the Mojoko simulator. And you can observe that for these two robots, we're actually executing the same action. And we manually measure the rope parameters to duplicate it in simulation. And there is still a huge sim-to-real gap, which is again to show that if you're gonna learn the full forward dynamics model, there's no way that the system can perform sim-to-real transfer. But the hope here is that the learned delta dynamics model, at least its general direction, is transferable. So to validate or verify that hypothesis, we tested the trained delta dynamics model in simulation with a variety of ropes in real world. So for example, in the second case, it's not really like a rope, it's a long piece of cloth that has much higher air resistance when you swing it. And in the second case, in the third example, it's a bullwhip that is much stiffer and also has non-uniform linear density. Both of the properties actually just straight out cannot be captured in our simulator, and therefore really require the system to generalize based on the real world observations. So here I'm just quickly going to show you some of the quantitative results of the converged policy or trajectory when for different ropes on the same goal. Right? So the first thing that you can observe is that the robot will really try to use very different actions for different rope in order to achieve the same goal, and that different action is used to compensate different rope dynamics. And in our paper, we actually provide like quite a detailed and systematic studies about to test on the generalization capabilities of the learned delta dynamics model. Right? So in particular, we try to test on the performance with increasing level of difficulties with the same trained model that is trained in simulation. So for example, we test on different rope parameters that is both interpolating between the training parameters and extrapolating beyond the training parameters. If you're familiar with machine learning, you probably know that extrapolation oftentimes is much harder than interpolation. And also we test on different real-world ropes with very different physical properties. And then finally, we also test with a robot with different hardware embodiments by basically changing the length of robot's last link. Right? So if you change the robot's last link, it basically changes all the mappings between the action and its effects, and that really require or force the system to adapt online. And here is just a few quick takeaways from our experiments. Right? So first, we noticed that if you compare to like the traditional system ID method, we found that it's actually really hard to learn optimal policy based on the rope parameters, even provided with the ground truth rope parameters. And in particular, it also has trouble generalizing to new ropes with different physical parameters. And we can observe this job, in particular for the extrapolation case, it really struggles with that. And similarly, we also find that it's actually not very easy to approximate the dynamics model, right? So we tried actually both the linear approximation and the heuristic error function, and they both shows a much worse performance, which kind of justifies as why we need to train a neural network to predict this delta dynamics. A linear model is not sufficient, at the very least that. And then finally, in the real-world experiment, we actually test with some very strong baselines. Basically, we try to optimize the action to get optimal action in simulation with measured rope parameters. Right? So this baseline or like this method should be able to give us the perfect results if the model in simulation matches real world. But again, it actually oftentimes shows more than 10 centimeter error, which again kind of highlights a big sim-to-real gap for this task. So now I'm gonna just show you what. Oh, question?
So in the sys-ID case, what is the model you are using?
So system ID case, we have two sets of experiments. So you actually have two models. One is identify the parameter, like the sys-ID model. The other is that once you have the parameter, train the policy. Right? So the first one we basically take the observation, predict, then regress the row parameter. like very simple, like I guess CNN. And then the second one is the MLP that's trying to like predict from the row parameter get the action.
Okay, both are learned models.
Both are learned models. And I think in particular, even if you give the ground truth, I think that highlights the real bottlenecks is even you have the ground truth row parameter, the policies are very hard to learn. It's able to overfit for your training data, but it's hard to generalize. Yeah.
Okay, how did you make it convenient to the projection depth? The projection depth of the scene.
Oh yeah, so that's a good question. We can actually kind of assume that the swing is on a 2D plane.
Okay.
Yeah, so we calibrate the camera, and then when the swing is out of plane, like it doesn't really work. So there's a lot of mechanical design to make sure that the whole system is stable and repeatable. Yeah.
Shuran, so for the rope case, I maybe this is my assumption or a bias. The dynamics will primarily depend a lot on the aerodynamics effects, right? And those are not modeled in the sim at all.
No.
Right? So did you factor that in? Is it a part of the system ID?
No. So aerodynamics is clearly something that didn't model in the simulator,
Right.
and then this may be one of the driven force of why all the simulation-based method is not working very well. And then, but I guess the thing that we showed is that the delta dynamics model, at least the general direction, is still okay, even consider aerodynamics.
You said like 4 iterations. Like what is 1 iteration?
One iteration is one action.
Okay, so you collect 4 swings, and that's how you learn.
Yeah.
You learn from scratch from those 4 swings.
So the model, it doesn't get updated at all. So the model is trained in simulation.
Oh, I see.
Yeah, and then in the test time, we only do the inference on predicting, like for different data action that you sample, try to predict the effect, and then do the sampling. The model itself doesn't actually get updated.
Wait, and what do you do with those 4?
Yeah, so the 4 iteration will give you a different observation, and it allows you to sample different delta action based on the current action.
Oh, got it.
Yeah, because the action space is really big, you cannot sample all of them. Yeah.
So the residuals here, like what you're learning is proportional to the velocities, like in the drag on the rope, right? And the rope mechanics. Also in the tossing part, the residual is where you grab how far is from the center of mass and whatnot. So do you have an intuition as to how far you can take this? Like what is the biggest residual that you can learn, which is most orthogonal to the measured states?
Yeah, so I think that's a very good question that I probably take more time to like really think about and go through that. But I want to repeat the question so that people can think about it, is that we actually show different ways to predict the residuals. Like tossing ball is actually the residual on the velocity of the tossing. And then here the residual is on the dynamics model itself. And then I guess the question really interesting to think about is that what is the general formulation of residual and how much we can deviate from the residual?
What is the biggest residual that you can learn? Like by biggest, I mean the most orthogonal to the measured states.
Yeah, I don't have a direct answer for that, but I think that's a very interesting question. Yeah, maybe we can discuss it offline. Okay. Yeah, so I want to show you one last experiment from this paper. Is that we're trying to really stress test this system with unexpected online interruptions. So what we did is that in the middle of the experiment, we try to mess with the robot by tying a few knots on the rope. Right? So this tying knot action actually changed a few critical parameters like the length and the density of the rope. And then immediately after this interaction, we can observe much higher error. But we can also, like after a few iterations, the system is able to quickly adapt with the new rope dynamics and then we get a good performance. So this knot tying accident actually happened quite often in our experiment. The robot cannot just swing and tie a knot. And we are surprised that the system can work. That's why we're showing you this result here. Okay, so to summarize, I think what iterative residual policy give us is a relatively general framework that's able to be applied to any repeatable task because we need to reset the states every time, but it can handle quite complex dynamics. Right, so I think the key takeaways here is that instead of trying to learn the full forward dynamics model that maps the action to trajectory, we can actually learn the delta dynamics model that maps the changes in action, how will affect the changes in the trajectory, which is like the gradient of this effect. And that is actually more generalizable to, like, for example, the noisy real-world dynamics and also unknown physical properties. But if we take a step back and really try to look at this project from a slightly more higher level, you can also see that like this IRP project as a very good example of how we can able to distill relevant knowledge from a highly inaccurate simulator, right? So in this project, I highlight again and again how inaccurate the simulator is, but this model learned from the simulator is able to help us to acquire some very precise manipulation skills. So I think this perspective is actually very useful when we think about larger variety or larger range of systems that involve complex dynamics that we may traditionally think is very hard or impossible to model or simulate, and potentially can open doors for many unconventional robot hardwares. And a good example for that is error-based manipulation. Right? So in this project, dexterity, we're trying to make the robot manipulate deformable objects by using active error flows. Right? So if you think about it, both deformable objects and aerodynamics are things that are extremely hard to model, and it's gonna take very expensive compute to model them precisely. But what we learned or found out is that instead of trying to learn the dynamics model or like try to model dynamics, it's actually much easier to train a policy, a closed loop policy that learn how to adjust, for example, the blower direction based on the visual feedback. And that is actually a much effective way to learn about effective policy to, for example, unfold a piece of cloth. Right? So in other words, although the dynamics is very hard to learn, the policy of how to adjust the action is much straightforward and easy to learn with visual feedback. So by the end of learning or training, we actually can see that the system is able to unfold a large variety of clocks, including the ones that's actually originally too hard for fling ball because of the speed limit. Right? So for this long dress, the fling ball is only able to unfold it in half because it reached the speed limit, but dexterity is able to like effortlessly unfold this cloth with just a single blow. And I think there's actually many other applications if you start to think about error-based manipulation. So for example, you can try to use error to open up a deformable bag or blowing leaves into a corner like during winter or fall. And then if you think about it, all these tasks is actually really hard for just traditional contact-based manipulation. Just thinking about how you can pick up the leaf one by one using your hands. But instead, if you like using error, you actually get a chance to kind of apply this kind of dense force field into a large 3D space without direct contact, and therefore make all this task a lot easier. So to summarize, I think both IRP and dexterity kind of show us learning a dynamics model, even inaccurate ones, can be useful for robot planning. And then we also clearly see that the models learned in today's simulator actually are very limited in their accuracy. But in both projects, we also show that we can use visual feedback, train a closed loop policy that potentially bridge this gap. However, another way to really think about this problem is that if you already have an active agent that's sitting in the physical world, interacting with the physical world, and also observe its interactions, can we just directly use all these interactions and observations to learn a world model from all these like rich sensory feedbacks? Right, so that is actually lead to the last topics for my today's talk, which is from skills, robot manipulation skills, to world models. So if we look at this topic, actually now we're going to look at a slightly different role of manipulation. Instead of just changing the objects or rearranging the world or changing objects' position, we're actually using manipulation as a very useful way to learn about this world. Right, so if you think about in your daily life, oftentimes you move an object, manipulate an object, not just for the purpose of changing its position, but instead you try to use this manipulation as a way to get more information about the object or about the environment. Like you open up this drawer just to see what's inside. That's an example. And then if we put this concept into a robot system, that's actually what's called interactive perception, right? So under this kind of a formulation, what we care about, like the manipulation, is not just merely a downstream application for perception, but also it can potentially provide a very useful supportive role for the perception algorithms to potentially build a better model of the world. So for example, we can ask the robot to interact with different objects in order to estimate their physical properties. We can ask the robot to, for example, cut through an avocado so that you can actually estimate the internal structures of the avocado, where is the core and what's the geometry of the core. Or interact with articulate objects in order to like infer the kinematic structures of the objects, right? Where is the joint and what's the joint parameters. Right? So if you look at all these examples, they are actually able to retrieve information that's extremely hard to obtain from passive observation alone, which again highlights the importance of having action in the loop. So today I'm just going to talk a little bit more about the first example, which is a project called Dense FizzNet. And so the goal for this project is that we try to learn about objects' physical properties, like their mass and friction, by training a visual prediction model. Right? So we have this very simple hypothesis. We think that if we train a model that's able to learn to predict objects' future state under different interactions or actions, the model should be able to acquire an implicit understanding about object's physical properties. However, one thing we learned through our experiment, or like something interesting we learned in our experiment, is that this hypothesis is actually not always true. Right? So it's actually highly dependent on the type of action that you use to collect the training data and to train the predictive model. So for example, if your robot only use quasi-static interactions, like slowly pushing the two blocks, then no matter like whether these two blocks has different physical properties, their motion in the camera is actually very similar. They always stop when your action stop. So as a result, if your robot only use quasi-static action to collect data, they not even have a chance to learn about the physical properties of the object. And similarly, because the object's motion is often jointly influenced by multiple physical properties, it really needs the system to use very different actions in order to decouple those physical properties at mass and friction. So to address those issues or challenges, in this paper, we actually designed two types of dynamic actions like sliding and collision in order to reveal different physical properties. And then this prediction model, again, we train it with self-supervised learning by basically using the camera looking down the workspace and then compute the optical flow as a supervision to train the prediction model. And here is a system in action where the robot is actually interacting with 3 different blocks with different physical properties. And then on the right, you can see the feature embeddings extracted from the neural network, each dot corresponding to 1 pixel, color corresponding to different objects. Right, so at the beginning, you can see that the feature embedding is actually very clustered together. They cannot really distinguish between different objects. However, through the more and more interaction steps, you can observe that the embedding space start to become more and more separated, which is an indicator that the system is able to learn object representation that encode the physical properties. And to further verify that, we actually trained a linear decoder or regressor that tried to decode the exact physical properties from those feature embeddings. And here is a prediction error with respect to the exploration steps, which shows that with more and more interactions, the system is able to accumulate the knowledge about physical properties of the object. And then when we compared with, for example, the system only use quasi-static action, we can verify that dynamic action is very important for really reviewing those physical properties. And then similarly, when we compare with the system only using one type of interaction, we also notice that the diversity of the action is also very important because that helps us to decouple the different physical properties. So I think what makes DAS-FISNet really different from the earlier examples I showed you is that what we're trying to do here is we're really trying to learn a general world model of the physical world that is not tailored to one particular task or robot action. Right? So in the paper, we actually shows that how we can reuse this learned physical properties of objects to apply it for a new task or new robot action that is not originally trained on. Question?
So it's a bit of a philosophical question, but there's a slight contradiction in this part of the talk and in the previous part. Because so far, you basically convinced us that it's a bad idea to find the parameters like this or anyway, and just have just some dynamics or interdynamics on the top and then get good results. But here, we're going back to kind of inferring the parameters. So how can I think of it?
Yeah, I still feel like inferring the physical parameter itself is not a good idea. So I think this is just an example that I think, so for example, with decoding the physical parameter like friction and mass, we don't necessarily need to decode that. It's just a way for us to evaluate the system, whether it actually learns that information, right? But I feel if you want to build a very robust system, I don't think you always need to go for the route of bottlenecking your system, predicting the physical parameters. I think the biggest limitation there is that mass and friction are useful, but maybe there are other parameters that are more useful that we are not decoding. So I think here we use that as an evaluation to see whether the representation is meaningful, but it's not necessarily the best way to go for application. But I have to say that if you have the parameter, if you have a physical model, it's more likely to generalize to new task.
So I'm thinking about the multi-agent extension of this. Do you think that there's, first of all, something that can be gained from the robot observing another agent that it doesn't have control over? And second of all, there seem to be interesting properties that you learn about the world only through cooperating with someone else. Like lifting a table. If I am only trying to lift a table on my own, I'm going to be convinced it's going to be too heavy. It's just not movable. But if I can actually do that with someone else, I can be like, okay, this is movable, this is not too heavy.
Yeah, I think that's a very good angle. Let me try to repeat the question a little bit. So what's the extension when we consider multi-agent? What if we can observe other agents' action? Can that help? I think definitely yes. I think that's a very interesting direction. But I have to say that there's also challenges come with that. Is that once you observe from a third-person view interaction, you don't have all the information, in particular the action information. Right? So here we actually, the network knows exactly what action you applied, and that's very helpful when you try to decode the physical property. When you're observing someone else doing it, you lose that information, and maybe that makes the learning a little bit more difficult. And similarly, when you have a collaborative setup, you really need to have a good model of how your agent is capable, like what is the capability of the other agent. I think that's actually applied for both scenarios. That's an additional challenge, but also open up new doors.
How sensitive is this paradigm to the error in measuring the states, optic flow, everything?
Yeah, so the question is how sensitive this thing is with respect to, for example, the optical flow prediction. I think it's probably quite sensitive. And also, like, if you notice that the friction and the mass we're decoding, it doesn't have a unit because it doesn't have a very good correspondence. We measure that in simulation, but it doesn't really have a very good correspondence to the real world physical parameters. So I think all those things is sensitive, and it will definitely influence the accuracy of the result.
Also, sorry to continue again. If you have like plastic, metal, wood, they would probably have different scales of mass. Maybe one is 1 kilo, one is like 1 gram, whatever. So when you estimate them, do you get like at least one scalar factor common, or is there a warp in that space too? Like what I'm trying to get at is, if one mass is 1, 10, and 100, do you recover that times one scalar factor, or that is one?
Actually, I don't know. But I think what we're trying to evaluate back then when we are doing this paper is see whether, for example, the ranking of the different properties is correct. And I'm pretty sure that the system will have, like, it's not that accurate, like because the supervision is so weak, it's just optical flow. It basically knows that who moves further, but it doesn't really have very precise measurement. Okay. Should I move on? Okay, good. So yeah, in addition to generalization, I think this is a good idea if you learn a word model. I think the biggest advantage compared to the tailored model is I can generalize better. And I think another take-home message I want to highlight in this work is that when you are thinking about training word model, the role of action is very important. And also even like the selection of the action is very important. You need to use dynamic action, for example, to even review the physical properties, or using diverse enough action to decouple them. If you just watch a random YouTube video, it's very hard to learn those information. So that is one of the take-home message I want to give you. Okay, so that is an example of how we can learn the word model from robust manipulation skill. And then if you look at the earlier example, basically shows us how learning different dynamics model is able to help us, even inaccurate ones, is able to help our robots acquire precise or new robust like manipulation skills. And if we put them together, you can see that we can treat this feedback loop as our general formulation for learning that robot intuition. Question?
I have another question about the parameters. Like in the previous case, you were inferring mass friction. But if a robot applies a dynamic force on the robot, how does the model distinguish? Is it because of high mass or high friction? Oh, sorry, low friction.
You mean how to choose the action?
As in, the properties are kind of conflicted with each other, right? Like,
that's true.
I have to apply high force because of high friction or because of high mass and low friction.
Yeah, so indeed, those parameters, if you're thinking about the application domain, so what you're gonna do, how we do it in the paper is that we plug in those parameters into a simulator again and use that as a model to plan your action. So you can sample different action and choose the one that give you the closer.
So you don't really care about if it got the exact friction or mass right, you just care about the effect with the same.
Exactly, yeah. And I think that's limited. We actually, it would be really cool if we can predict very precise mass and friction, but it's limited by all these errors in the system. So in the end, we only care about the relative ranking. Yeah. We also discretize action, so it's easier to predict. Okay. Yeah. So this is the general formulation that I'm thinking about as learning the robot intuition. So if you really thinking about how to move forward, I think the answer is quite straightforward. We really want to think about ways that we can accelerate this feedback loop and potentially enable this flywheel effect towards what we call the human level dynamics reasoning. Right? So this is clearly a very hard problem, and there's so many things that we need to work on along this path. Like for example, how to collect data in a scalable way, or how to do this and that. But I think one of the most very critical steps that we were aware of is we need to have a more general way of modeling skills or learn robot skills, right? So in a lot of projects I showed you today, and also a lot of questions actually got mentioned, is that we, for a lot of success that's in our projects, is actually contribute to this manually designed action primitives, right? So we design this tossing primitive, this fling primitive, or even like this swing primitive. So all this action primitive is actually very useful when you apply learning for those robotics problems, because it helps us to map those very complex action sequence into a very low dimensional action space, and therefore it helps the learning problem. Therefore, you can actually learn them with limited amount of training data. But however, that design of like action primitive, as you guys all can imagine, is very limiting because it requires a lot of expert engineering and also manual tuning. And I think even more a bigger problem is that this kind of pre-designed action primitives with parameters is not general enough to potentially represent all possible robot actions, especially the ones that requires high-rate reactive behaviors. Right? So for a while, actually, our lab has been like really searching and looking for a general policy representation or action representation that could potentially encompass a broader range of robot interactions or behaviors. And I think I really feel pretty excited to share this idea, or like this work, is that recently we think this is very promising to use diffusion policy actually as a universal skill representation. So for example, without going into detail, I can show you like all these different examples of robot behaviors is actually trained with diffusion model that is using the same network architecture without manual tuned primitives, and the system is able to directly learn those behaviors directly from data or like from the raw sensor input. Right, so, and in particular, if you look at the second case of the mark flipping task, you can see this robot actually organically switching between like pick, place, and even pushing actions in order to achieve the goal. And oftentimes it's also able to recover from like, for example, grass failures. So all this like intricate behavior is really hard to code up if you just like limited yourself to primitive designs. And then, yeah, so basically how we're able to achieve that is basically collect training data with teleoperation and train a diffusion policy to fit that training data. So what diffusion model really give us is basically a very powerful way to like precisely model those very complex distributions in the robot behavior or human demonstration data. And so in particular, one good example is modeling this kind of multi-model distributions. Like for example, if you have multiple ways of doing the same task, diffusion model is a very natural way to actually precisely model that distribution and give you a good action trajectories in the end. And it also has other good properties, like for example, it scales very well with high dimensional output, and also it's relatively stable to train, so that you don't need to like keep checking which checkpoint is better. That's like a pain in robotics. So I think that makes it a very practical framework to scale up like human like learning from demonstration systems. So after diffusion policy got published, actually our friends in TRI really try to scale up this framework. They actually collect, I think, hundreds of different tasks, and here is just a subset of the tasks that the robot can do with this very simple framework of doing diffusion, using diffusion policy to fit demonstration data. And we really think that the system is very far from reaching its limit. So I think that's why you should really try out diffusion policy on your system as well. If you're learning any policy, I think you can use diffusion policy as a baseline. And then to do that, we actually has like released the code, and in particular, this collab, we really try to simplify the whole system to like less than 1,000 line of code to go through a complete example, so that you can get the concept to learn like the framework without all the complications of the framework. So please give it a try and let us know if you have any questions about it, and we are happy to like improve it further. And then, okay, so with that, I want to end my talk with just a few closing notes. So today I talked a lot about manipulation. I think in today's audience, probably a lot of you work on manipulation for a while. And I think this is really an interesting robotics task. It's so hard, but at the same time, very intriguing. But however, if you look at the literature, I think for a very long time, we have been defining the task of robot manipulation as the task of rearranging objects through properly selected context. But what I really hope is that through today's talk, I can give you a little bit of new perspective about this classical problem, especially if you treat dynamics as part of the solution, not the problem. Right, so for example, we can start to think about manipulation beyond context. Like for example, using accelerations and error to control those out-of-context surfaces. We can also extend the role of manipulation. Instead of thinking about it as a way to rearrange our world, it can also be a very useful way to help us collect information and know about our surrounding environment. And then finally, we should also rethink about the way we model dynamics, right? So oftentimes maybe it's impossible or not necessary to have this perfectly accurate model, but instead we can make use of those inaccurate physics model or simulator and combine it with visual input to achieve precise and adaptable manipulation. And then finally, I really hope that all this example can help us to encourage us to rethink the way that we design the robotic system in general. Instead of avoiding dynamics, I really hope that we can start to embrace dynamics. And with that, I want to end my talk and thank all my collaborators, funding agencies, and most importantly, all my students from Columbia, now all in Stanford, make all this project possible. And here is actually a drawing from my students I drawn about our lab's research, and you actually can see some of those examples like fling ball, like air paper in the top, and I feel really, really lucky to be able to work with all these amazing students in my lab. And I'm happy to take more questions.
I have a question about the frequency of adaptation. On the IR's paper, it's like an episodic adaptation. You execute a sequence of action, you find the like the gap between the end effector to go, and then you adjust it. But in fact, as humans, we can like feel the weight already changes at the very first half of the iteration and change my action in the second half.
You think so, yeah. But not necessarily. Actually, so I think at that time when we were working on that project, we actually did a lot of study about how humans do this highly dynamic task. And one thing that we found kind of surprising and maybe not counterintuitive, but like surprising to us at the beginning is that we human actually the control loop is not that high frequency, it's about like 5 Hz. So first, a lot of tasks like swinging a rope, we are doing it open loop. But I think for robot, it doesn't really need to limit it to our capability, right? So I think we do it in a more open loop fashion. Doesn't mean that robots don't need to able to plan in a more high rate. So I guess back to your question is that possible for the robot to adjust their action in the middle of it with the feedback? I think yes, but we will need a better sensor. We'll need, for example, a force sensor or tactile sensor instead of just a visual feedback in order to achieve that higher rate control.
I see. I've got another question on the control part. So as for Embodied, it's a hard-coded policy, and as for IRS, it's a initial action already set up. And as for the diffusion policy, it's based on expert demonstrations. But what if you incorporate reinforcement learning into your pipeline? As for Embodied, for example, you already decouple the problem by detecting the position to grab, and also and then do the following up action. But what if you use reinforcement learning as the control policy? Well, yeah.
You mean I guess you're trying to say that using reinforcement to replace the primitive design? I see. We didn't try that. Mostly because we think that if you use reinforcement to learn the primitive itself, it's gonna take a lot of data to get that. So we kind of just take a shortcut by manually designing that. But we did apply reinforcement learning in some other aspects. So for example, the fling ball case, when we are predicting the fling velocity, we actually train a reinforcement learning algorithm to adjust the fling velocity. And it's indeed able to improve the performance. And if the robot is more capable, I think we can see the improvement on top of just single step prediction a lot more. So I think that is a valid direction to go. And then using reinforcement learning to learn the primitive skill, I think it's an interesting direction, but it's kind of hard to make it work with the current technology. And learning from demonstration has been shown a very powerful way, at least to initialize all this learning. Yeah.
Thank you, very inspiring.
Thank you. Okay, maybe you first.
Yeah, so very great talk, thank you. So I think somebody already asked this, but the primitives are hand designed, and I'm thinking of this fling action or this toss action as a very neat trick that humans sometimes use to achieve these tasks very successfully. And you mentioned that maybe this diffusion policy can learn those tasks by having some expert data, but probably scaling that up and learning these key tricks might be very difficult for wide varieties of tasks. So how do you think we can go about addressing that problem?
Yeah, that's a very good question. And if I ask you, so I think the observation is totally correct. For example, using diffusion policy to learn different skills is hard. But if I ask the question one layer deeper, which part is hard, right? I think the hard part is getting the right data.
Yes.
And then, so getting the right data, why is hard? If you tally off your robots, it's really hard to get those dynamic actions. So the question is can we learn from more straightforward, maybe human videos or other type of data to acquire those skills? But then you have a embodiment gap to address. So I think that is a very interesting direction, and we are working on a little bit of that. Yeah.
I see. And the second question is
maybe since we're out of time, let's take one last question, and then she can stay here for longer.
Okay.
Thanks for the great talk. I think I have a high-level question about the problem formulation of those robot learning tasks. Like a lot of your previous work trying to formulate a family of tasks by some action primitives, but we also think that diffusion policy has more general action-based setup. Do you think in the future, a large-scale generalist robot learning, should we focus on the more general setup or some human prior knowledge of the task itself?
That's a question I wish I know the answer. Yeah, it's a very.
Your opinion on that.
My opinion on that. I guess it really depends on how urgent you want your system to work. I think if you want your system to work next 5 years and you have a startup out of it, I'm happy to code the primitive. I'm happy to code the primitive so that it's very robust and it's able to handle the narrow scenarios that I care about. As we show that it's possible, for talking about Flingbot. But if you really care about the general intelligence agent that are able to acquire skills and do any task, I would say going for a more general route, general action formulation, and ask them to be able to use that general action representation to learn different skills. I think that's more in long run, it will be a better solution. Yeah, but it's gonna take more time, gonna take more data, and probably take more research work to do it. Yeah.
Thank you.
Okay. So with that, let's thank Shuran for an amazing talk.